Hey guys, we're in section 6.1. We are almost done after we get through this, but I want to make sure you understand what you're actually doing when you do these. Let me put it this way. I could show you how to do the problems on this page in about 2 minutes. You would have no clue why you're doing it. You could probably generate the correct answer, but that will definitely not help you if you are studying for the AP Calc Summer Packet. I need you to understand that you know so much mathematics by this time, but I want to make sure you put it all together. So some of you guys might fast forward through this and go straight for the practice, but when you're working through the AP Calc Summer Packet and you're stuck, it's because you fast forwarded through me. Just let me lay this out so you can wrap your mind around it. It will help in the long run when they get more complicated. So I have an example here. It says inverse of a function used in a trig setting. Well, the first problem does not need an inverse. It doesn't. This is something you did back in geometry. They gave you a right triangle. They gave you a right triangle, and they gave you some information about it, and then they said something like this. Find the value of x in feet. Now, do notice here, I have my angle given in degrees in my picture, so if I was going to use my calculator, which, by the way, I did, I had it set in degree mode to make this easier. But I want to find out what x is. So I look at this and I say, you know what? This angle appears to be opposite that side, and then I have an adjacent piece of information. They didn't tell me anything about the hypotenuse, but I don't need to know it if all I want to do is find out what x is. So you guys hopefully remember this from geometry. I would say tangent's the function for me here. If I take the tangent of that 32.2 degree angle, it will be equal to the opposite over the adjacent, which is a proportion. And I can solve a proportion by making it look like that, cross multiplying, and I say 1x, or x, is equal to whatever 24.7 times the value of whatever tangent 32.2 degrees is. And I did that earlier on my calculator, and I got x is equal to 15.55 feet. What I'm trying to get at is this. Tangent, cosine, sine, all that stuff. It's not only just good for right triangle, trig, find the missing value. Oh man, you guys have seen there's a whole big world of stuff we do with sines and cosines and tangents, etc. There's all kinds of stuff we do with it. It gets more and more as you go through AP Calc. That's why we have to get through so much information with trig. But we've been doing tangent of some given angle equals some ratio. We've been doing that all the way up until now. But remember, they taught you this in geometry too, so I'm going to go through one of these. This is the other side of the coin, and this is the motivation behind our lesson today. This is where they give me information about the sides of this right triangle, but they don't want to know about the missing side. They're not asking me to use Pythagorean theorem. They want me to find the value of theta in degrees. Now, they could say radians, but I just picked one, and my calculator was already in degree mode, so I left it there. And I look at this and I go, wait a minute. Well, it looks like there's an opposite side from my angle, and it looks like my hypotenuse is involved. So I could start off and say, well, the sine of that angle, I don't know what it is, but the sine of that angle has a particular ratio, opposite over hypotenuse. But the thing is, that tells me what sine theta is. Sine theta is a ratio. I don't want sine theta. I want theta. So this is the trick they taught you way back when in geometry. They said this is when we take our calculator, and remember on your calculator you got a sine button, then you got this thing right above it. That is not cosecant, right? I told you guys this really early in the lessons. This dude is called the sine inverse. And you guys have seen this in action. We use this a lot. If you take a function and you compose it with its inverse, as long as you do this to both sides, I should have given myself more room, what do we get on this side? When you take f inverse of f of x, or like I showed you on the summer packet, they're going to write it like this, f inverse of f of x, you get x. When you compose a function with its inverse, you get the variable. So sine inverse of sine theta, you get theta. Now, what's sine theta equal to? Or what is say theta equal to? It's equal to whatever this numerical value turns out to be. But what I'm trying to get at is, when we are using an inverse trig function, we're talking about an angle. We're talking about an angle. So I punched sine inverse into my calculator. I did sine inverse of 71.3 divided by the other guy, etc. And I got theta equals 67.1 degrees. That's what I got for my answer. So the world of trig now goes inverse function. And when we see sine inverse, cosine inverse of something, when we see that kind of stuff, whoa, what the heck did I do? Undo. I don't know what I did. Please go away. I don't know. I'll figure it out, I guess. Hang on, guys. Let me try something. I don't want to have to restart this. Okay, let's go back. Not now. Boom. Hey, it went away. Okay, good. Anyway, when we are doing trig with inverse functions, we're talking about degrees. Now, here's the thing. I remember having to show you this. So here's the other part of my intro. If I give you something like y equals 2x plus 1, that's a linear function. I can switch x and y. I can solve again for y. And I can say this guy's the inverse of the other dude, right? One guy's the inverse of the other. And remember, if I called the first guy f of x, and I called the other guy f inverse of x, and I did f of f inverse of x, if I compose them, it means plug one of them into the other, so that would mean 2 times this plus 1, and what would happen? Cancel, cancel. I'd get x minus 1 plus 1. What's the... Whenever you take a function and compose it with its inverse, you get the variable isolated. And that's how this works when we do this sine inverse thing. They didn't tell you it was function composition back in geometry. No, that was my job to get you to that point. But when you have an inverse of a function, sometimes it's like this one here I made up, where it's a line and then it's a different line. And if we graph them, we can do, hey, let's draw the graph of this. And then, hey, 2x plus 1 looks like that. And then x minus 1 looks like that. And then there's, hey, the line splits it down the middle. That inverse check. Now, that is a horribly quick graph I just drew. But what I'm trying to say is we talked about all this stuff. And when we talked about this stuff, we also had to take it this next level. Let me go one more here, because I want to make sure you get this underlying concept. And all of this stuff that we're doing right now that I'm doing for you, Something like y equals x squared plus 2. Well, y equals x squared plus 2 also has an inverse. As long as I put a restriction on it, it has an inverse. What? Yeah, we haven't done this in a while, but as long as I put a restriction on it, it has an inverse. Because remember, if I draw this picture, I would say it's a parabola that's up 2 units. And I could draw that parabola. I totally could. But this parabola is not 1 to 1. 1 to 1. If I draw a vertical line and I hit it in one spot only, it's a function. That's cool. That's on your AP Calc summer packet. But if I draw it with a horizontal line and I hit it in more than one spot, it means it's not invertible until I restrict it. So what was my restriction here? I only want to look at the part of this graph that is bigger than or greater than or equal to 0, which means I want to take this part away. Well, why do I do that? Well, if I switch x and y in this situation, right? If I switch x and y, and then I solve again for y, ready, okay. I would get y equals plus or minus rad x minus 2. Well, I know how to graph a parent function. Rad x minus 2 means go 2 units to the right, and I would graph it like this. And then when I draw my splitter, bam, it cuts it down the middle. My graph is symmetric on both sides of that line, which means I got to take away this part. That's not going to help me. I only want this part. Why? Because I need the restriction and this to match up, because one of these guys' domain is the other guy's range. Let's take a look at this. I'm going to call this guy my red dude. Hey, red guy, and you might go, whoa, where'd the trig go? I'm getting there. I got to get there. But that guy, let's call him the red graph. He has a domain. He does. Bracket 0 to infinity. He goes that way forever. He also has a range. The lowest point on him is at 2, and then it goes up 2 to infinity. Now, for two functions to be inverses of each other, one guy's domain has to be the other guy's range and vice versa. So let's look at this. Let's call this guy green graph for a second. The green guy has a range. The green guy's range, well, the range would be the lowest number on it and above. This guy, the green guy, also has a domain. His domain would be, well, it starts here at 2, and then it goes that direction. So what I'm trying to get at is, you can only have an inverse function, and this is review. You can only have an inverse function if these conditions are met. One guy's domain is the other guy's range, and vice versa. And you might be saying, well, where's the trig? Well, here's the thing with this. If I want to, and I'm going to get a black pen again. If I want to look at my graph, I'm just going to do a couple of these and then just tell you. If I look at y equals sine, right? This graph, sine graph. Well, when I sketch it, I like to start here, go like that, but boom. But it goes like this too. And it goes on forever and ever in both directions. I can draw a vertical line in a bunch of different spots. I only hit it once. That's a legit function. But if I try to draw any horizontal line, smack, 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 smacks, I would hit this thing infinitely. So the thing is, when it comes to a sine graph, I have to make a restriction if I want to find its inverse. So this is what we're talking about. if I wanted to have the lowest point on any sine graph, oh God, this is not a, where did I start? No, wait a minute, I drew a cosine graph. Oh crap. The same point still exists, guys. I'm not going to restart this lesson. Let me try better here. But what the concept is the same. My stupidness is different. Or did I start? No, I did. That was my x-axis. I'm okay. I'm okay. That's where my y-axis was. There's my x. I'm not starting over. But here's the thing. This graph, if I look at it just from here to here. Oh, God, really? From here to here. Will it pass the vertical line test? Can I draw vertical lines, only hit it once? Yes. What if I draw horizontal? Oh, I'm not going to have any repeats. So this is partitioned on a sine graph from negative pi over 2 to regular pi over 2. If I just make that be its domain, if I restrict it and say, you can only go from here to here, then the range will go as low as, what's the lowest point? The range will go as low as -1. It'll go as high as +1. So we say if you want to find the inverse of this function, you're going to have to restrict it so that you're only looking between 0 and pi over 2 or 0 and negative pi halves. Here's what the chart on page 253 is trying to tell us. There's a chart on page 253. It looks like this. Boom. If you have a sine function and it's taking the sine of some angle x, and you want to work backwards and find out what the angle was to get that, you can't be looking everywhere all over this graph. You can't be looking everywhere all over this graph. What we do is we cut it off so that it passes the horizontal line test. We partition it in a certain location, and then we can invert it. Now, this is the part you really have to focus on. If I draw a sine graph and I chop it from here to here, I chop it from here to here, that is the same as looking in either quadrant 1, because that would be 0 to pi over 2, or looking in quadrant 4. That would be negative pi over 2. So when we start looking at our questions, they're going to say something like this. Sine inverse of something equals 1. And I'll go, oh my gosh, where would that happen? Well, I would have to do this trick. And then I'd say sine of this. And then what happens on this side? Cancel because of the composite. So I'm saying x equals sine of 1. Hey, where is sine equal to 1? Sine is equal to 1 when that angle is pi over 2. Pi over 2 is part of quadrant 1. Remember, it's included. That's a bracket, not a parenthesis. That's a bracket, not a parenthesis. So what we're going to be doing is we take the concept of an inverse. Some functions, sine, cosine, tangent. In fact, every single trig function has to be restricted to invert it. So when it comes to sine questions, we only get to look in quadrants 1 and 4. When they give me a cosine question, when they give me a question about cosine, our answers are always going to be in quadrant 1 and 2. When they ask me a tangent question, 1 and 4. Then, take a look at this. Secant. Secant goes with cosine, so it's 1 and 2. Cosecant goes with sine, so it's 1 and 4, just like sine. But be careful here. Cotangent has different asymptotes than tangent, so don't think what works for tangent works for cotangent. That's different. You have to think back of your graphing days, way back when we were drawing these graphs. If you draw a tangent graph, those are its asymptotes. If you draw a cotangent graph, those are its asymptotes. So they are different from one another. They're not the same here. Now, this might sound a little confusing, but as we go through the practice problems, you're going to see me partition, and I'm going to refer to this. So this box right here on page 253, if you have it out when you're watching the next video, it's going to become clearer and clearer. Why did I go through all this background? Well, because you know this is truth. You can find a missing side if you know the angle and you know the trig. But you can find the missing angle if you know the sides and you know the trig. But all the stuff they taught you in geometry was in quadrant 1. Everybody was a quadrant 1 angle, so they never had to go through anything special with you. But now we're talking about invertible functions. If you can find the inverse, then it should pass the horizontal line test and all that stuff. Also, when you compose functions, you should get out the variable, that concept. That's on your AP Calc summer packet. Then, this was my motivation. Some functions do not have an inverse unless you restrict them. So you restrict their domain so that you can find an inverse for them. That's when we start thinking about a sine graph must be broken down where it passes the horizontal line test. Where do we break a sine graph? Right here and here. What would that be? That would be, if I were to graph it, that's quadrant 1, that's quadrant 4. That's that concept. So, this chart, this is the meat of it. This is what you really need to help you answer the next couple sets of questions.